Welcome to this part of our XPS for Beginners course, the Data Analysis 5, and we're going to be going through some stuff on doublets and how we would look to process these. So if you remember back to our fundamentals course, we talked a bit about some XPS peaks that produce two peaks or a doublet due to spin orbit coupling. And we mentioned that this is actually pretty useful because we can use that to process data which might otherwise be a little bit tricky. And so in this session today, we're just going to be looking at how we could do that in practice. So I'm just going to go across to Casa and open up our practice example. So we'll provide this file in the description or on our Guru page. If you're watching this on YouTube, follow the link in the description to our Guru page and you'll find more resources there. So if we can scroll through these and see that we've got lots of 1s orbitals, which are single peaks or multiple peaks that are ready to be deconvoluted. And then if we go across to d or p orbitals, we start to see that we do indeed have some of these doublets that we're going to need to figure out how we can resolve and fit properly. So I'm going to go through a quick example first. This is nice and simple, it's just silver, so there's only two peaks that we need to think about here. So we mentioned in the previous video that we can use the regions tab in quantification to set up our background. So I'm going to just stick a Shirley background across these two peaks very quickly. You'll notice here that when we've applied this, we've got our backgrounds kind of cutting through the spectra of it here. So we'll actually have to apply this as two separate regions, two separate backgrounds, just to avoid cutting through that data. So there we go. Just drag this along here. Right, so we've got our regions in place, we've got a background drawn, so we can come across to the next tab now, components. So we've already seen a bit on components so far, so there's not much new in this part. I'm just going to click on create a couple of peaks for us here. I'm just going to turn off some options just to make it a bit more visible. So yeah, similar to before, we can drag and drop our peaks into position, get them roughly in place, hit fit, and that will line them up as they should be. So there's a couple of options we can do here, but the simplest is going to be if we look at our two columns here. So we've got the descriptive parameters for peak A, this red peak here, and peak B, this green peak here. Now the three important boxes here, or most important I should say, are the constraint boxes. So we've got the ones in yellow. These are what we're going to use to make sure that our spectra fit properly and make sure they sort of obey the theory behind how they arise. So the first thing we can do is just apply a peak modifier to our area. So if you remember back to our fundamentals course, 3D peaks, we should have an area ratio of 2 to 3 or 2 over 3 to from the 3D 5 over 2 to the 3D 3 over 2. So if we go into our 3D 3 over 2, in fact I'm just going to label these just so that everyone's clear on what I'm referring to at all times. We can come into our area constraint of peak B, and we know that this should be 2/3 the area of peak A. So you can either type in that or you can type 2 over 3 and it will do the conversion for you. So we've got a lock in place now. This area ratio isn't going to change. We drag this one, the other peak is going to be dragged with it. So the second one we're going to look at is the fourth half maximum constraint. So you'll remember we discussed again in the fundamentals course that we should try and keep these the same at all times, barring a few notable exceptions. So I'm just going to type a times 1 into that one, and now when we change the fourth half maximum, just drag and drop that there, you can see again this peak is now using the same fourth half maximum as this first peak. So whenever I change this, the second one changes, just like when I change the area, the second one changes. So the only thing changing now is this energy position, which is independent. So if we just go to fit again, so there's, for a situation such as this where we've only got two very clear peaks, you don't have to put in anything here. You can just fit the components. You can see the difference between these energies here. There's a bit of a quick way to check what that is. If you type in lock, that will automatically set this to a position, or an energy difference based on the current peaks. Or you can use a value from literature or theory. So I mean, this is pretty close to 6 anyway, but generally use an energy difference of 6 when modelling silver peaks. We can put in a plus 6, and then if we were to move these around now, whenever we change the area, the fourth half maximum or the position, the 3/2 peak will now follow and then mirror what the 5/2 peak is doing. So we're just going to click fit there. Now if we wanted to use these in another model, so this is silver carbonate, so say we wanted to model some form of silver carbonate in another system, then we would be wise to also keep our binding energies in one position. So one little trick that you can do here, so you can come down to this position constraint, so we're at 365.44ish. If we were to come down here, we could manually type in 365.2, 365.6 and hit enter, and we've got roughly where we are, plus or minus 0.2. And now if we try and move these, we can't move that more than that limit that we've set in the position constraint. But a quick way of doing this, if you type the hash key into here and type 0.1, that's going to give us a plus or minus 0.1 EV either side of where the peak currently is. Hit enter, and that will set up these limits for you automatically. Similarly for the fourth half maximum, if we were copying this into another system where we might want to look at silver carbonate versus silver metal content, say we give ourselves another 0.1 plus or minus, we can then copy this model into a second spectrum, and we've got our peaks locked together as they should be. So our area, fourth half maximum and position constraints between the two peaks are locked, and also the absolute values for fourth half maximum and position are now going to be locked in place. So we can just slot this into another model, another spectrum, and we can have a silver carbonate representation there. So that's the basics of how we would look at a doublet peak. I'm going to just move on to an example for titanium. So this is one of those examples that we've spoken about where the fourth half maximum of the 2p1/2 isn't the same as the fourth half maximum of the 2p3/2. So if you want to learn a bit more about why this is, I put a link in the description and on the Guru page to our article on Costa-Kronig transitions, which goes into a bit more detail about why you might get broadening of a peak in a doublet system such as this. But we're just going to quickly mention a little bit about some of the pitfalls of using these constraints and how we might look to model a system where we've got different fourth half maximums. So what we didn't look at in the previous example was there's also this function create times 2. So we can just click on create times 2, we can drag our peak around over here, and we can click fit. Now obviously normally this would then fit the data quite nicely. So for example, if we go to calcium up here, click on create times 2, click on create times 2. It fits the data pretty much exactly. We've got that area ratio of 0.5 and the 4th half maximum the same. But again, with titanium, because we don't have the same 4th half maximums, this default model doesn't fit. So if you use this function, you just need to remember to clear that constraint, and you can do that by coming down to the 4th half maximum constraint and just typing in new limits. So say we just use the default 0.2 to 5. Click fit, and now that fits a lot better. So the area constraint is still the same. We've still got a 2-to-1 ratio of the 3/2 to 1/2. And this is also, we'll say 4+. So this is just some anatase titanium dioxide. And what we can also do is come down here and put in our doublet separation. So if we want to use this as a model for, say, titanium 4+, we can use the similar functions before when we used the link function, or the lock function rather. If we use the link function, so if we were to say put in lots of peaks, all of the same species, so this is, for example, probably best explained if we look at, say, a carbon. Just going to come here, put in a bunch of peaks, roughly the right positions, and if we try to fit these, we're getting quite different 4th half maximum. If you then come here and type link, you can tell Casa to set every single column to the value in whichever column you typed in link. So we typed link into the 4th half maximum constraint of A, and this is then set the 4th half maximums here to A times 1 and A times 1, and now we've got a bit more of a more accurate model. So if we come back to our titanium, instead of typing link here, we're going to type lock, and that's going to lock the 4th half maximum modifier to whatever the difference is between the 3/2 and the 1/2 peak here now. So now if we try and, I can select it, change our 4th half maximum, this is going to change as well, but it's also going to be always 1.8-ish times greater than the 4th half maximum of the 3/2 peak. So that allows us to keep our consistency with the 4th half maximum when we're modelling, but also account for this difference in the 1/2 and 3/2 due to the cost of Koenig. So to give you an example of why that might be a bit more useful, I'm just going to put in, so our component index here is a nice way of keeping track of what species is what. So it's quite useful for doublets, it's very useful for when you come to do multiple splittings. It just allows you to kind of tag, so we're going to tag titanium 4+ as component 1, and then I'm just going to add in a new component here. So this is going to be titanium 2p 3/2 3+, and I'm going to give that component index of 2. So this will be roughly down here, and we can, in fact, we come to our position constraint. We know from literature that the titanium 2p 3/2 for 3+ is about 1.5 EV lower than for 4+, so we can put in A minus 1.5 here. The area constraint we can leave, this is that's a variable that we're trying to measure. And then we've also got 4th half maximum. So one thing, so the first thing to note, we've put in these component indexes. So if you try and do any lock functions now, it's only going to apply to the same component index. So when we add another one, this is kind of separate from what we've done previously. So we need to just add in our modifiers manually. So although we've got different 4th half maximums between the 1/2 and the 3/2, when we come in to add a new species, so for example 3+ here, we still need to keep that consistency between the 4th half maximums of the individual doublet peaks. So when we are adding our new 3/2 peak, we're going to keep the 4th half maximum between the 4 plus 3/2 and the 3 plus 3/2 the same using this a times 1 modifier. So I'm just going to add in our final species now. So this is the 1/2 of the 3 plus contribution. So the first thing we're going to do is we need to lock the area of this 1/2 to the area of the corresponding 3/2. So for the 3 plus 3/2, I'm just going to add in c times 0.5 because that's this column here. C is the 3/2 for 3 plus. Change this component index to 2. Now for the 4th half maximum, instead of locking it to the 4th half maximum of the 3/2 for 3 plus, we're going to lock it to the 1/2 for 4 plus. So what we're saying is the 4th half maximum for all of our 3/2 peaks are the same, and the 4th half maximum for all of our 1/2 peaks are the same. So if we type b times 1 in here, it's automatically going to simplify that down. So everything will be a times something. If it's, if this is a dependent of this, then, and this is a dependent of this, then it's just going to default this to being a dependent of this. So finally we will stick in our doublet separation. C plus 5.7. So we've got the same doublet separation, but these two peaks are going to be offset by 1.5. So 1.5 lower than these two peaks here. Our area constraints for both of our 1/2 peaks are the same. Our 4th half maximum of our 3/2 and our 1/2 are equal. And then we've got our position constraints here. So C plus 5.7 and A minus 1.5. So if we then go to fit, we can see our 3 plus contribution down in this kind of pre-peak area, and our 1/2 in the kind of integrated into this broadness. It would be something that would be very difficult to deconvolute if you weren't using any of these parameters and these constraints. If I come back up to display parameters, if you come to display parameters and colors, if you've been using component indexes, you can type fill component index, combine component index and color components using the component index, and that just gives you quite a nice way of visualizing where the peaks are and which peaks relate to what in doublets and multiplets and so on. So it's quite nice if you're exporting these spectra as images. We'll go back to fit. So there's a bit more work to do in terms of tuning the line shape here, so this is not necessarily a particularly great fit. It's more just to kind of introduce you to using these component indexes and using them in a slightly more complicated system. So do feel free to give those a play. We will provide this VAMAS file in the description and on our Guru page. If you want to know a bit more about the doublet parameters, so if you want to find a bit more information about the individual parameters of specific orbitals, there's a lot of online resources. The NIST XPS database is obviously great. XPS Fitting run by Mark Biesinger is another great resource, as is XPS Simplified from Thermo Scientific, and obviously we've got hardwellxps.guru as well. I'll just give you a quick example of XPS Simplified if you've not seen it. So it's just a page for zirconium here. We can see we've got a couple of examples of some binding energies, and then down in the interpretation section they've got some a value for the spin orbit coupling, so the spin orbit splitting. So we've got 2.4 eV doublet separation there. So there's plenty of resources around, and again we'll link those in the description. So to summarise, always use constraints. It's going to make your life a lot easier, and it's also going to make your fits better. Be careful with your 4th half maximum constants. Keep them obviously constant where is possible and sensible. but also be aware that there are those cases where it doesn't necessarily stay the same, and it's just something to be mindful of. And also there's plenty of literature resources around where you can find information about all the kind of doublets and orbitals in XPS. So up next is going to be some video on asymmetric peaks and line shape parameters, so enjoy, and I will see you again.